The starting point for modern growth literature is the Solow model, or sometimes Solow-Swan model. The model is based on the assumptions of neoclassical theory and thus takes us away a little bit from the Keynesian and new Keynesian business cycle models we've covered so far. It was independently developed in 1956 by Chicago economist Robert Solow and T.W. Swan. The model is also sometimes referred to as exogenous growth model because it is at core a model about what doesn't explain growth. So in some sense, growth is exogenous, and this may seem a little bit unintuitive, but by understanding what cannot cause growth, we can focus a little bit more on the question, what can cause growth? The core insight of the Solow model is that accumulation of resources, that is the buildup of, say, capital or education, and especially the buildup of capital, cannot explain long-term sustained growth. The reason for that is the law of diminishing returns. That is the feature of resources to become less productive at the margin, the more of them we employ, which causes a bottleneck to growth. Now, the Solow model is a model of long-run growth, and it departs from the assumption of the neoclassical model, in the sense that it starts there, not that it changes them, which for all practical purposes you can think of as the production model that you have learned in microeconomics. And I know that's a fun lecture. Unfortunately, we're going to have to come back to this a little bit. If you think within these constraints, output, which is simply everything we can produce, GDP on the aggregate level, depends simply on the resources we have to produce them. And this includes labor, obviously, it includes capital, it includes land, education, and so forth. In the most basic version of the model, we focus only on two production factors, that is capital K and labor N. The core in question this intends to answer is, how does investment, which is the buildup of the capital stock over time, contribute to a nation's productivity and to its growth? It is not difficult to add other productive factors like human capital to make this model a little bit more realistic, but to drive home the general point about what role resources really play in growth, it's strictly not necessary. Instead, we simply assume that output y is some function f of k and n of capital and labor. I will for now not place restrictions on the specific function here, but any standard microeconomic production function, like for instance the Cobb-Douglas function that showed up a couple of times by now, will do. The function does, however, have to be well behaved, and what this means from an economic perspective, it needs to have diminishing returns to both capital and labor. That's a fairly standard assumption. It describes the physical process of production. And for simplicity of dealing with the production function, we're also assuming constant returns to scale. Notice that we use n as representing the total amount of employed workers, as represented by the equilibrium level of employment. As a neoclassical model of the long-term growth trend, the Solow model ignores cyclical unemployment. So that's something we leave out, and I'll say a few more things about this in a few minutes. Since we're interested in GDP per worker, which is the concept that really drives GDP per capita, we can simply divide the output production function by n, and that gives us output as a function of capital per worker, y over n. To do so, we can divide every single input factor by n. K over n is k over n over n is 1. So we end up with productivity, how much one worker can produce, how much one worker on average contributes to GDP, as a function f of k of n and 1. It scales, obviously, in the population size. Now, one of the reasons why we can do this, and I'll add a practice problem to this, is the assumption of constant returns to scale. Other than that, this function becomes a little bit more complicated, although it doesn't necessarily qualitatively change. Of course, as I mentioned earlier, the other standard assumptions still hold. Capital per worker still shows diminishing returns to scale. Let's simplify the notation somewhat. Y over n is equal to lowercase f of k over n, where f of k over n is simply defined as f of k over n and 1, the function we had earlier. This is an identity. The only thing we're doing here is we're just simplifying notation. I don't want to carry around this one term here. It doesn't really do much otherwise. What this is saying is that, well, output as a function of capital per worker is a function of capital per worker. It's really just an identity. Since we're interested in time, we're interested in growth, I'm adding time indices as well. And specifically, I'm adding one to Y and I'm adding one to K. So output over time is going to change and capital over time is going to change. What is implicit in this, I'm not adding a time index to N. That means that the population size, the labor force participation rate, and the unemployment rate are all assumed to be constant. This again is just a simplifying assumption. You can change this fairly easily, but it adds additional dynamics. We'll talk a little bit more about population growth later on. The consequence of this is that employment is constant. If employment is constant, output per worker, output per person, and overall output are simply proportional to each other. So the only thing we will be changing in this model is the capital stock overall, and we can answer how that in isolation affects output and how it affects growth. And then we can add bells and whistles earlier. It's just a very stripped down model in that sense. The second assumption, which is not as obvious but is critical, we are assuming that there is no technological progress for now. Intuitively, that means the two production functions that we have, lowercase f and uppercase level f, do not change over time. So the way that capital per worker contributes to output per worker does not change. A hammer is a hammer, and there is no technological progress here. Now that we've established our basic assumptions and relationship between labor productivity and capital per worker, we need to think about the question how capital builds up over time, which is what economists call capital accumulation. If you want to extend this to other factors of production, like for instance education, we broadly speak of factor accumulation. That is the buildup of productive resources. Now capital intuitively increases through investment, which is the purchase of new capital. By the same token, capital also breaks and becomes obsolete over time, and that is what we refer to as depreciation. Investment adds to the capital stock over time. Depreciation reduces the capital stock over time. Now, when we think about investment, we have to ultimately think about saving. And modeling saving comes down to policy and behavioral analysis, which isn't always trivial, but for now we can just handle it as an accounting definition in the interest of simplicity. We know that by definition, investment equals private plus public saving. I is equal to S plus T minus G. We've been over this a number of times through the course, of course. To keep the model a little bit more manageable, we'll ignore public saving for now, again, coming back to that later. And in this scenario, investment then simply equals private saving. I equals S. Behaviorally speaking, saving rates can vary across countries, for instance, on things like demographic differences, like the population's age distribution or cultural norms, and less growth itself. And as a consequence, realistic modeling of saving behavior can be somewhat tricky. For now, we do bypass this particular problem because saving needs to come out of income. And on a macro level, it is thus simple and safe to assume that saving is some fixed, constant proportion of outcome. It's simply a fraction of outcome in the most basic version of the Solow model. Formally, saving is then simply a fraction S of output Y. So for instance, if S is equal to 20%, then 20% of GDP is saved, which flows into investment in new capital, and this is what equation 8 expresses. As a numeric example, if GDP, for instance, is 20 trillion, at a savings rate of 20%, a country would save 4 trillion each year. With this assumption in hand, we can turn to the dynamics of capital accumulation, which as mentioned is simply a function of investment and depreciation. Specifically, the capital stock at the end of a period, KT plus 1, is equal to 1 minus delta times the capital stock at the beginning of the period, KT, plus investment IT during the period. Delta here indicates the rate of depreciation, again some percentage, and depreciation is simply a physical process. Stuff breaks through usage, machines fall apart, this sort of thing. Capital breaks at a specific rate, which isn't behavioral for that reason. The common estimate on a macro level for developed markets is something around 2% per year. To summarize the intuition behind equation 9 one more time. The capital stock at the end of 2020, for instance, is the capital at the beginning of 2020, 1 times K T, minus depreciation of that capital stock during the year, delta times KT, plus investment throughout 2020, IT. For instance, say the original capital stock KT is 100 trillion. At a depreciation rate of 2%, this capital stock will shrink by 2 trillion throughout the year. If investment were say 5 trillion, at the end of the year we'd be left with 100 minus 2 plus 5 equals to 103 trillion worth of capital. Finally, we express capital accumulation in per worker terms since we're interested in per worker productivity and output, not just general capital and not just general output. Dividing equation 9 on the previous slide by n, and then substituting in our expression for investment as a fraction of output, we get the capital stock at the end of period per worker as 1 minus the rate of depreciation times the capital stock per worker at the beginning of the period, plus investment per worker, which is the fraction of output per worker the economy sets aside during the period. Depreciation, original capital stock, investment during the period. Bringing the initial capital stock to the left hand of the equation then gives us the change in capital stock per worker, which is simply investment saving per worker minus depreciation of the original capital stock per worker. Apologies about the lowercase letter y here. This is a typo. That's the same y as here. So the change in kt plus 1 divided by n over kt n is equal to the fraction s times overall output. This is our investment per worker minus the rate of depreciation times the original capital stock, which is depreciation overall during the period. Let me give you a silly example. If the average worker in our model economy had 100 hammers, this is the capital stock per worker, the change in the number of hammers per worker is how many new hammers we buy per worker, say for instance 10, minus the number of hammers that broke per worker. If the depreciation rate were 2%, that would be 2. So the change in hammer stock in this silly example would be 10 minus 2, which is 8 additional